Today I'm going to solve the problem number 5024. This is the problem where we need to establish the formula for number of elements in the power set of an arbitrary set. So let's suppose we have a set of different elements a, I, and the cardinality of this set, so the number of elements in this set, it is a finite set and it has m elements. We have to prove that the cardinality of the power set, and the power set is a set of all subsets, is 2 to the power of m. Just to give you an example, let's suppose we have the set of A and B, then power set of A, which is the A and B, is 0 set, or which is empty set, set consisting of A, of B, and A and B, the set A itself. So we have 4 possible elements, and 4 is 2 to the power of 2, where 2 is the number of elements in A, as given A and B, 2 elements here. So yeah, that's a pretty simple example. If you consider the set where we have like 3 elements, A, B, and C, you can do pretty much same thing. You can see that we have the empty set, we have A, we have set of just B, we have set of just C, and then we have set of A and B, and then we have set of A and C, and then we have B and C, just kind of combinations of different elements here, combinations because BA and AB are the same thing. The elements should be kind of, we disregard the order doesn't matter, so that's why we need distinct elements. So, and the remaining one is ABC, which is A itself, and then if we try to calculate the kind of the number, try to count the number of subsets here, we can see that we have 8 subsets here, which is 2 to the power of 3, which is exactly 2 to the power of m, where m is the cardinality of A, which equals to 3. Cool. So these are just 2 simple examples. And how should we go about solving this or proving this problem? So one of the simplest possible ways to prove this problem without relying on advanced math is just, well, interpret these elements like this. Let me build a simple visualization or intuitive table which could clarify the method that I'm going to rely on here. So this is the elements A1, A2, A3 until AM. Since we have m possible elements in the set, they are all elements of our set. And then I'm going to denote here the zeros. Now let me just extend this a little bit. I'm going to add am minus 1 as well. 0, 0, 0 until 0 and 0. That means 0 means we do not include this element, and 1 means that we include this element. So we have m cells, and each cell can have one of 2 possible states. 0 state is when we omit this element, and 1 state when we include this element. So we have 0, 0, 0, that means empty set. This is the equivalent of saying that we have empty set. And then we can have 1, 0, 0, and until 0, 0. That means we included the first value, it's like A1, and then we can say that 0, 1, 0 until 0, 0, and this is equivalent to saying that we included the second element, and then going the same way we can reach the state when we have, like, oops, sorry, oh Jesus, I guess that should be like this, 0, 0, 0 until 0, 1, which is equivalent to saying that we have only a mth element, which also belongs to this initial set. And now we can do the same for the first 2 elements, like 1, 1, and 0, and so on. And then we, like, taking all these possible permutations, we can reach a situation when we have 1, 1, 1 until 1, 1. So we have kind of the table where each cell can be represented by 2 possible states, 0 and 1. And based on our combinatorics or combinatoric rules, we have the product rule, and the product rule essentially states that the number of possible permutations would be like the number of possible states for each cell multiplied together and found the product. So this is going to be something like number of possible states or number of permutations here. Possible permutations here is like for the first cell has 2 possible states. That means 2 to the power of, just 2. And then for the second cell we have 2 possible states, and then for the third cell we have 2 possible states, and then until we have mth cell, and mth cell also has 2 possible states, which is 2 to the power of m, because we have m elements here. We have this kind of rule because of the tree rule, tree law. You can visualize that for the first cell, you can have 2 possible states, 0 or 1, and then for 0 you have 0 and 1, and then for 1 you have 0 and 1, and then for 0 you have 0 and 1, and the same 0 and 1, 0 and 1, 0 and 1. So you're kind of just listing out all possible states for each possible value here. This is like 2, and for the 2 you have another 2, so this is like just 2 states, and then 2 times 2, and then 2 times 2, and then again 2, and then you have 2 times 2 times 2, and then again 2, kind of recursively until you reach the bottom of the recursion, mth step, right? And at the bottom of the recursion, you have 2 to the power of m elements. So this is the product rule in combinatorics, and this is one of the major applications of combinatorics here. You can apply the combinatorics in order to find the cardinality of the power set. So that's the whole problem. We basically proved that and visualized this result using, using apparently combinatorics. So that's the whole problem.